Over the last few years, web services have become the most popular way of distributing functionality in the cloud. And in this video, we'll look at how we can model a web service and test it. So I'll talk about web services in general, just to introduce the idea first. Then I'll describe an example web service based on a test application I use in my workshops. Then we'll talk about modeling and testing the web service itself, and I'll give you a demonstration of ARD in action in this way. And then I'll close and discuss some of the issues raised in the demonstration. Now, according to Wikipedia, a web service is a service offered by an electronic device to another electronic device communicating with each other via the World Wide Web, which isn't so helpful. The essence of it is that we have software applications that communicate across the internet, and they make use of typically the web protocol, HTTP, to communicate. Now, there are many types of web services and styles of operation of these things, but I'm going to look specifically at what are called REST or RESTful services. And there are many commercial organizations that offer free to use APIs to their services, like Google, Twitter, Facebook, and so on. RESTful services use HTTP or secure HTTP or HTTPS, and one of the characteristics of RESTful services is they are stateless. Every call to a service is atomic. There's no carrying over of state across these calls. They have several other architectural capabilities, but these aren't relevant for our demonstration. REST is the most common architecture, if you like, for web services, but we'll not look into the architectural properties of REST in much more detail. What I'll do, though, is show how Agile Requirements Designer can be used to test a web service, and I'll show you a simple RESTful web service example. Now, RESTful web services are called using the standard HTTP, HTTPS web protocol. So it's very easy to demonstrate RESTful web services using a browser, because we can put the parameters in the URI itself. Now, we know that HTTP is used for downloading web pages, images, files, music, videos, and so on and so forth. And also, when we create data, we post it, if you like, to services running on web servers to capture data in databases and so on. So although web services are intended to be used by web or mobile pages behind the scenes, services can also be used by other services. So we can have a hierarchy of web services or a network of web services which together in concert deliver some user application. Now, all common programming languages have features to construct web service calls, to make calls to web service, if you like, to handle the responses and interpret the response data. So whether you're using Java or C++ or Python, all languages have capabilities to create drivers of web services for the purpose of testing. Of course, there are some commercial tools available as well. Now, the demonstration web service I want to show you, I will demonstrate it through a web interface, and in fact the web interface to the service looks like any other application, a web application. But behind the scenes there is a web service that delivers the functionality, that performs the calculations. Now, the program I'm going to show you is like a triangle testing program, and like all testing consultants, I've got my own which I use for demonstration purposes in workshops for exploratory testing, for example. Now, in order to use this, we need to look a little bit further at the geometry of triangles. So I'm sorry to deflect the discussion from test design to geometry, but it's only for a couple of minutes to give you a sense of how the application works. So the way the triangle program works is it accepts three numbers, which are the lengths of the three sides of a triangle. It validates the numbers you enter, or the text you enter, and it checks that the three lengths provided can make up a triangle. You can construct a triangle. I'll show you how this works in a moment. If it's a valid triangle, it calculates the area, it checks whether the triangle type is equilateral, isosceles or scalene, and I'll show you these in a moment. It also checks whether the triangle has a right angle in it, And if you remember Pythagoras as to how you calculate the length of sides in a right triangle, it'll use that formula. And if the sides of the right triangle are all integer values, it's what's called a perfect right triangle. So a triangle we can consider, say, 3 sticks on the ground, of lengths 4, 6 and 12. And if I lay these out, usually the largest one first, I cannot construct a triangle using those 3 numbers, those 3 lengths. So 6 and 4 add up to less than 12. The longest side is longer than the other 2 sides. So the validation that's going to take place is to check whether one side is longer than the sum of the other 2 sides added together. So the validity checks are basically whether one side is greater than or equal to the length of the other 2 sides, the sum of the other 2 sides. Because actually if the length of the longest side is the same as the sum of the other 2 sides, you basically get a straight line, which is not a triangle. So the checks are always whether one side is greater than or equal to the sum of the other 2 sides. There are 3 checks to be performed. Now the next thing is to check whether we have an equilateral triangle where all 3 sides are the same, A equals B equals C, where the 2 sides are equal, and it might be the 2 longer sides and you end up with some kind of spiky kind of pyramid, or the 2 shorter sides are equal, where you have a flatter kind of pyramid if you like. So isosceles is where A equals B or B equals C or A equals C, but there's a third side that is not the same as the other 2. All sides different, it's called scaling. So in this example I've got a triangle with sizes, lengths of 6, 7 and 8. That's a scaling triangle. So none of the sides are equal to each other. These are the checks that the program is going to perform for us. The next check is like a right triangle, whether it has a right angle in the triangle at all. Now we know from Pythagoras that the square of the hypotenuse is equal to the sum of the squares on the other 2 sides. So the check we're going to perform is whether the square of one side is equal to the sum of the squares on the other 2 sides. So if you look at this triangle, it's a 3, 4, 5, a classic triangle used in maths classes. You can see that 3 squared plus 4 squared does equal 5 squared. It's 9 plus 16 equals 25. So this is the kind of check that would be performed by the program. Finally, if all the 3 sides are integers, it's called a perfect right triangle. Of course, the sides of the triangles could be 0.3, 0.4 and 0.5. They wouldn't be integers, but it would still be a right triangle. Finally, and I won't dwell on this, there's a calculation that can be done based on the 3 sides of the triangle called Heron's formula, which gives you the area of the triangle. And I'm not going to talk about this except to say there is a formula that will be used to calculate the area by the program. Now, the program itself I can demonstrate as a web application on this link here. So if I just go into it, you'll see that there's a self-signed security certificate. Don't pay any attention to that. It is a harmless website, I promise you. So here is the triangle web page. I'll make it a little larger so you can see what's going on. So you can see I have 3 sides, A, B and C. So if I put in my right triangle, 3, 4, 5, submit, I get a result you can read here on the top, but it's also duplicated down here in the text here. So I could put in a triangle I know not to be correct. So I had 12, 4, 6. Oops. This shouldn't be a triangle. Not a triangle. Side A is larger than side B plus side C, and that's okay. So that's my web application. So if I go back to the presentation again, I should say there are some bugs in the program, which is not a bad thing for a demonstration program. But the purpose of the program is to help teach people exploratory testing, but we can use it here to look at the web service that sits behind the screen you're looking at. So if we go to that, there's a web service call here which will provide exactly the same functionality that you've just seen. So if I click on this, it should open my browser again. I get the same warning. And what you see here in terms of the text, if I just make that a bit larger, this response is in a format called JSON, JavaScript object notation as it's called. And essentially it's a way of packaging up data to separate the names of parameters or results and the values of those parameters or those results. So for example, I've got a result here, right triangle, which has a value. Angle C is a right angle. I've got another response parameter, result, A equals 3, B equals 4, C equals 5. Triangle is scaling. These \n's are new lines. So this is a text response, isn't it? Next one, triangle type. The colon indicates what follows is the value. Triangle is scaling. Triangle area. The area of the triangle is 6 units. Perfect right triangle. This triangle is a perfect right triangle. And the sides just mirrors back the values that you supplied. A is 3, B is 4, C is 5. So you can see that depending on the values here that I provide to the web service, I will get a different response. So let me just show you this again, but with a value that would not be correct. So we have A is 3, B is 4, C is 5. Let's make the long side much longer. Let's make it 9 than the sum of the other two sides and try that. I'll hit return and I get the result, not a triangle. C is larger than side A plus side B, and so on. So you can see we have the essence of a web service, and we can test it using the browser. Now we can't do that with all web services. It's just an example in this case. So just to explain how web services work in a little more detail, in our example, I wanted to show you how a web service can be called using a browser to demonstrate it. So you can try out the service for yourself and have a play, and perhaps find the bugs as well. Usually, with RESTful web services, the parameters are supplied in the body of the HTTP message. Now you'd have to do that programmatically or using a driver or a test tool. Now in this demo, we haven't looked at web services that use the Simple Object Access Protocol, or SOAP. We haven't looked at XML, and I could have used XML, but I think JSON is a simpler, more compact way of looking at the data. And we could also have used something called WSDL, this web services description language, which is used to specify service interface definitions. So these are, if you like, extensions to the most fundamental kind of web service, and REST pretty much is the simplest kind of web service. Now, whether you're using SOAP, XML, WSDL, whatever, it doesn't affect the way you design your test cases for a web service. Okay, we're back in ARD now, and I want to show you this model I called REST Triangle. Now this model is the overall design for the web service parameters of the three sides supplied to the triangle, but I want to show you what I've done at the top of the model first, of course. And I've created a subflow called valid triangle, and what this does is validate the data to say whether it is a valid numeric or whether you can create a triangle from the three numbers. So let's just open this in another tab. And in effect, there are 6 checks. So just to go through them very quickly. Firstly, I want to check whether the first value, A, is a valid number and greater than 0. So a triangle cannot have a 0 length side, of course. I've got the same check for B and the same check for C. If any of those are false, we get invalid input. Next, I check whether the longest side is less than the sum of the other two sides for all three sides in turn. So I've got A less than B plus C, B less than A plus C, C less than A plus B. If any of those are false, we don't have a triangle. We can't construct a triangle from the three sides. And obviously, if you get through all the 6 checks, we have this valid triangle outcome. So going back to the original model, what that does is it simplifies the top half of the model with the validation completely separated from the rest of the model. if I have an invalid input, or I have the not a triangle outcome from the valid triangle check, I come straight down to the bottom, and that's the end of the process. So let's look at everything given that we've got a valid triangle. So the first check I perform is whether it's equilateral. So if A equals B and B equals C, the three sides are the same, I've got an equilateral, and that takes me down to this location here, no right angle. Clearly, if all three sides are the same, there can't be a right angle. It's the same shape triangle, whatever the dimensions. Okay, so if it's not an equilateral triangle, we then check whether we've got an isosceles, and we have these three checks. A is B, B equals C, A equals C. If any of those are true, we have an isosceles. Otherwise, clearly, all three sides are different in size. We have a scalene. So for isosceles and scalene, we then check whether we've got a right angle triangle. We have the three checks in turn, whether a squared equals b squared plus c squared. So this is the Pythagoras theorem that we're using just to check that the longest side, A, in this case, does not equal the sum of the squares of the other two sides. I've got to check for b squared equals a squared plus c squared, and then finally c squared is a squared plus b squared. If none of those are true, we have no right angle. If any of them are true, we then have a further check, are A, B and C all integers? And if that's true, we have a perfect right triangle, and if that's false, we have a plain right triangle. If we have no right angle, or whether we have a perfect right triangle or a right triangle, we then calculate the area, and that's the end of the process. So overall, that's the shape of the model. Now there are a couple of constraints that we need to look at. So if I go into constraints, certain paths cannot coexist. So this first one I want to show you, if A equals B, if side A equals side B, then clearly the check for the Pythagoras theorem, b squared equals a squared plus c squared. If A equals B, then C must be 0. That's impossible. So this combination of A equals B and then b squared is a hypotenuse in a right triangle can't happen. There are two of those, A equals B, that are separated. B equals C, I've got two of those, and then A equals C. So there is 6 constraints, which basically eliminate the possibility of two sides being the same and the third angle being a right angle. So let's close the constraints. And if we look at the validation again, so if we go to Path Explorer, I'm going to look at all possible paths, as always, to start with, and I get 7 paths. And this makes sense. There are 6 validation checks. There are 6 ways of failing those validation checks and 1 successful outcome to say that the data and the numbers used can be used to create a valid triangle. So I'm going to save these paths, and we can also, if I close that, look at the data for this model, and you can see there are the 7 test cases and the values for the various checks that are done by the model. So let's save this. And this will cause the parent model to have a notification saying the subflow has changed. So I'll go to that and we'll reload subflows. And now let's look at the Path Explorer, and as usual look at all possible paths and see what this gives me. Okay, so I get 23. Now the first 6 of these are the 6 paths which the subflow detects either bad data or an impossible triangle combination. And then the remaining 17 paths reflect the valid outcomes of whether it's a right triangle or isosceles, scalene, equilateral, and so on. So 23 tests sounds about right to me, so I'll stick with that. So I'll save those paths and close that window. And now look at data. So in here we should have the 23 test cases, and you can see all the validated data from test number 7, and the first 6 are the failure examples. And you can see the data that comes from the subflow is in purple. So you can see that's from subflow data there. So we now have our 23 test cases, and that gives me some confidence that we've got a covering set of tests that is sensible for this web service. I want now to make some observations on the triangle model I've just shown you and the testing and test cases that result in the analysis we've done. You'll note that in the test data there are some columns that represent relationships between test values rather than literal test values, if you like. For example, to see whether we have a right triangle, we need to check whether the square of the hypotenuse is equal to the sum of the squares on the other two sides, a squared equals b squared plus c squared. But also there might be a requirement to have a scalene triangle, which means that the sides A, B and C are all different, and we showed examples of that in the paths that we generated. Now there's an infinite number of values for A, B and C that satisfy these relations. Now we can choose values, whatever values they are, to make these relations true or false or whatever the requirement is. The relationships set some constraints on the values we choose, and we have to pay attention to this in creating actual real test data for our tests. In the actual testing, we are free to use any values we like to meet the needs of the conditions or the relations that we're going to check for. There was no requirement stated that related to the numbers, the scale of the numbers that we should use, whether very large or very small, but also the precision of the numbers. So, for example, an equilateral triangle could have a very large or very small value. So, 1, 2, 3, 4, 5, 6, 7, 8, 9 as a size of one side, and use that for sides A, B and C, would be perfectly legitimate to test whether the checks for an equilateral triangle are done correctly. By the same token, we could create extremely small values, and again, the check for whether the three sides make up a triangle legitimately, it's irrelevant how large these or small these numbers are. By the same token, an isosceles triangle could have two extremely large sides that are equal and one very small side. And the rules of triangles allow for this. Now, in our computer program, the ability to handle very large and very small numbers, there are limitations on what we can achieve in some programming languages. So this might be a set of tests that we add to refine or enhance our list of test cases to cover these circumstances where we have to deal with an extreme range of values in the numbers. In the model of the triangle program that I've shown you, the decisions made are based on combinations of relative values between parameters, between the three sides of the triangle. Now this is quite common, but it's usually more often the case that a web service or software in general deals in the literal values of individual parameters, if you like. Although I've shown you a less common situation with respect to this relative value idea, the way we test a web service is no different from other functionality that you can describe in a similar way to traditional requirements. Using ARD to model software programs, web services are just another style of functionality delivery that we can model and test using the outcome of our ARD analysis. Now in this case we used a simple RESTful service to demonstrate, but all web services work in a similar way and can be modelled and tested in a similar way. Now, when it comes to testing web services, they don't have usually a user interface. So we have to write some code to run tests, or use a dedicated test tool or driver to programmatically test the web services. The technicalities differ depending on how the service works, but the modeling and test design is consistent across all these styles of web service. One other thing is that the sequence or delivery sequence of parameters provided to the service should not matter. So that's not a consideration in our modeling. If you know the validation and processing rules, you can create tests that cover both the input validation processes as well as the legitimate and valid data processing rules.